Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Future of Stormwater Storage. My name is Megan Purdy and I'll be your host for today. Firstly, in keeping with our customs, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders past, present and emerging. Before we get started, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, ACCO. ACCO in Australia offers an extensive portfolio of stormwater, building drainage systems, cable pit and ducting systems across access covers and other niche products. The company has just celebrated 25 years as Australia's foremost manufacturer with facilities in Western Sydney and takes pride in providing excellent customer service along with extensive technical support from specification to the finished product installation. Today, we will hear from two speakers followed by our live audience Q&A session, and I encourage you all to send through your questions via our YouTube chat box, which you can do during today's presentations. I'd like to welcome our first speaker today, Ihsan Bahram. Ihsan is a senior engineer and hydrologist with more than 10 years of experience in the field of stormwater drainage, track drainage, hydraulic structures design, hydrological simulation, integrated flood management and flood analysis. He is now working as a senior engineer at WSP. Ihsan has been engaged in designing and simulating numerous service drainage network as lead drainage engineer for stormwater networks, including OSD, rainwater tanks, pump stations and different softwares such as drains, SWMM and sewer gems. He is also intimated with the water-sensitive urban design since he has worked as a hydrologist and is familiar with the natural water cycle. Please join me in welcoming Ihsan Bahram.
Good afternoon, everyone, and thank you for the introduction. My name is Ihsan, and I work as a civil engineer in WSP. I'll be presenting a bit of future of the stormwater storage, and I'll try to make it as quick as possible, not to bore you too much. So I just need a couple of words before I start. So WSP Australia, WSP is one of the world's leading engineers professional service consulting firm, bringing together approximately 6,100 talented people across more than 50 offices in Australia and New Zealand. We are technical experts who design and provide strategic advice on sustainable solutions and future-ready engineering projects that will help societies grow for lifetimes to come. Acknowledgement to the country. WSP acknowledge the traditional owners of the land on which we work, our offices and sites where our projects are planned, designed and constructed. The Gadigal of the Eora Nation are the traditional custodian of this place we now call Sydney. We honor their ongoing spiritual relationship with their country and continuing connections to culture, community, land, sea and sky. We pay our respect to their elder past, present and emerging leaders, as well as all our Aboriginal and Torres Strait Islanders staff members. Thank you. Okay, so I will be starting the presentation with a bit of a history of water storage and in general water engineering, evolution of design, the design challenges that we have, and recent innovations, and I'll finish off by some safety moments. History of water storage. As I was going through to get some resources for this, actually I was very amazed. We have a very long history of drainage and water storage. Lots of historical ancient civilizations has developed engineering, sophisticated drainage infrastructure and storage throughout the history. So I'm just gonna go through quickly a couple of them. Indus civilization in India, they had lots and lots of complex open channels constructed in the center of the street. Persians, they had, because it was an arid area, they had lots of urban drainage systems as well. They actually enacted laws to protect it from pollution as well, which was very impressive. Roman empires, they had significant urban drainage, road drainage, construction of large underground conduits, and they were pretty advanced on that. Incas traces, actually this came from our technical director, and I didn't know about this, but these civilizations in South America, they had these very massive traces with, they use it for land farming, but to help it against the erosion, and because they had received lots of rainwater there, the subsurface of the traces were very well planned engineering system. Like they had, just like us for water infiltration, they had soil, fine sand and gravels, and medium gravels. So that was very interesting for me. And then we, through the history as we come forward, we, in the past 200 years, there were lots of things that affected our design. So here is a summary of the improvement in the 19th and 20th century. We have improvement of pipe materials, construction method, maintenance practices, decision to use water carriage system of wastewater removal, comprehensive sewer system, combined versus separate sewer systems, identification of waterborne diseases, introduction of wastewater treatments, advances in urban hydrology, computer advancement that gave us a tool to do lots of complex calculations, and then finally the environmental awareness. So we move on to the next bit, which is the evolution of design. So I just want to speak a little bit about when this was started 30, 40 years ago. So there was this pre-development versus post-development. In this pre-development, when we have a natural catchment, we have a bit of rainfall, bit of evaporation, a bit of runoff, and lots of infiltration. As we developed that catchment in urban development, cities, and urban infrastructure, we still receive a bit of rain, and now the climate change a bit more. There is still evaporation, but as you can see, the infiltration has been reduced significantly, and instead we have lots of runoff. So if you look at this hydrograph here, we have a post-development hydrograph with versus pre-development hydrograph, which we can see this post-development has increased significantly. So to control this, we become with a couple of ideas, and the most popular idea was detention basins. So this detention basin, this definition is from Urban Storm Drainage book. Detention basins, also sometimes called retarding basins, are measures which temporarily store stormwater to reduce peak discharge. Outflows are typically controlled by a low-flow pipe, orifice, or a culvert, and a high-level overflow spillway for events higher than 1% AEP. And of course, there is detention tanks, usually we use above ground, underground. Both of them are very popular, but It's just that the storage of that volume of the water and releasing it gradually into our public drainage. And then we come with a different kind of detention basins, regional detention, which serves multiple properties, sub-regional, which has facilities that serve multiple landowners, and then we have on-site detention, which is generally serves one lot or a couple of commercial industrial sites. So here is a bit of design evolution. So we started with the underground, above ground tanks. Then we've moved on to combined above ground and underground tanks, combined rainwater, OSD tanks. So rainwater reuse came into the picture, combined water quality and OSD tanks. And then as we advanced, then it was natural detentions, ovals, wetlands, rain gardens, and then recent years we have modular tanks, geo-storage, green areas, roof gardens, natural bodies. So we are getting closer and closer to that environment-friendly solutions. So what does the detention basin do? So it's simple words. It reduces the peak hydrograph and it delays the hydrograph. So we are gradually releasing water in a controlled manner to reduce and to delay the peak hydrograph. Couple of design challenges that I'm pretty sure we all faced. Location of the detention tanks, that's or detention storages, that's always a challenge for the designers. Special allowances, we all need a big, very big tank usually, depending on the impervious areas that we have. Sizing and optimizing, it's a challenge. Tailwater level can be sometimes a challenge. High tailwater level will impact the design. Climate change has become into the picture in the last couple of years. And then, of course, maintenance and access, it's a very important aspect of the design, and it is a design challenge that we all need to consider. Next, so we have this, we needed a bit of more innovation. So where this recent innovations comes into the place. So what do we want actually in a innovative design? We want it, of course, to be safe, environmental friendly. We want to reduce the cost. We want that to be hydraulically efficient, easy maintenance, and of course, we want to improve water quality, which is very important for us. So based on what we mentioned above, there are a couple of concepts that has formed, and I really like these two definitions: best management practice and low impact development. So I'm just reading it from the definition. Best management practice, a device, practice, or method for removing, reducing, retarding, or preventing targeted stormwater runoff constituent, pollutants, and contaminated contaminants from reaching receiving bodies. What is low impact development? Low impact development is a comprehensive land planning and engineering design approach to managing the stormwater runoff with the goal of mimicking the pre-development hydrological regime. LID emphasizes conservation of natural features and use of engineered, on-site, small-scale hydrological control that infiltrate, filter, store, evaporate and detain runoff close to its source. So what is this saying is that we as humans, we came to the nature, we created a footprint, and by incorporating these methods, we are trying to minimize that footprint. So to be as close as possible to the natural environment. So some of the key LID techniques here, conserve existing amenities. So if you have an old tree, if you have a green area, park, land, natural pond, we are aiming to conserve that. Minimizing impact, we try to not to disturb the catchment as much as possible with cut and fill, regrading, so we just want to keep things as natural as possible. Permeable pavement, they have come into picture pretty much in recent years. Green roofs, minimize directly connected impervious areas, like you probably have seen some grass buffers, grass swales, and rain gardens, of course. So these are the key low impact development techniques that we are after in terms of stormwater drainage. There was a couple of design improvements as well. We have introduced high early discharge. That's just like a little small detention inside the detention to get that head over the orifice, so we can use the full capacity of that pipe or the orifice. Absorption trenches are now popular. Of course, you have to look for the site conditions. You can't have it on any soil. You just have to have a soil with a high permeability. Pervious pavement, and again, it's a very popular technique. These all have pros and cons, so it's you have to analyze the site condition before, of course, incorporating them. Geocellular models, modules, they come into picture. I'm pretty sure John will explain to us a bit in a moment. These geocellular, but they're just honeycomb structures that use to store water in urban areas. We have geo-storage. That's another innovation that we had in recent years that comprises a large open chamber formed by geogrid reinforced. This is a good option as well because it improves water quality. So this is another option which can be used. And then we have these precast tanks, or they call it storm traps. When you have the time is a constraint, these are very popular because they can install these very quickly. So this is a good option as well. What else we have? Yeah, as we're getting toward the end of the presentation, I just wanted to share this. I took my car for the service the other day, and it was raining. And this is the driveway entry to the repair shop. So if I play this, you can see that there is water coming in, and there is a grated drain here, but it's not capturing any water, right? So all of this I wanted to emphasize is that we need to consider constructability. So what we see in the drawing is not what's happening in the reality, and you can see the water escaped from the this curb and gutter, and it's captured in the downstream somehow, but it's just that this aerated drain doesn't do anything. So whenever we're doing the design, we always need to consider constructability as well. So that was just a interesting thing I came across, so I just wanted to share with you. Safety moments. Last, I want to emphasize some safety moments for you that I encountered. Consider maintenance for confined space when we are doing the design, when inspecting pits in the road, be aware of the surrounding traffic, watch for insects and spiders, bats. When inspecting covers for tank basins, ensure the outlets are clear of blockage and obstruction. Always have a torch and a laser measure. Do not use metallic tapes for measuring pit depths. Yeah, you don't know what's down there. Maybe a cable, maybe HV cable, LV cable, we don't know. So please consider that. And I just want to thank Alex, Steve, John, and Brendan who helped me prepare this presentation. And I just want to thank you all for listening to that presentation. And I know hand it to John to explain this the Aqua storage solution for us. Thank you very much.
Thank you, Isan, for your insights. I'd now like to welcome our second speaker, John Sordo. John has a degree in civil engineering with a master's in business administration and heads up the marketing and product management department at ACO. He has several years of product development experience and has launched numerous water and cable management products for the civil engineering industry. John has also pioneered a number of technical services, both web-based, and leads an in-house team to support the design community for the integration of technical and compliant products into engineering designs, and also looks after the marketing function for ACO. Please join me in welcoming John Sordo.
Thank you, and hi everyone, and welcome to our presentation on geocellular tanks. Before I start, I want to thank Isan and the EA team for their help in making today's webinar possible. And over the next 25 minutes, I'm going to describe the role of these plastic tanks, their characteristics, and offer you a guide on how to specify them. Underground tanks are used in lots of projects as councils legislate to protect their downstream waterways and infrastructure. Managing both the quantity and quality of water being discharged off a site is only going to grow in importance, particularly as cities urbanize and rainfall events intensify as the climate changes. These days, larger areas of the built environment are being covered by impermeable surfaces, which of course increases the risk of flooding. Tank solutions are a conventional way to stop and slow down the surface water runoff to pre-development rates, as well as replenish the groundwater at a more natural rate. These are the system elements that are designed to work with the natural water cycle. On a slab, drains are typically positioned to intercept or collect stormwater runoff, which is then treated or cleaned to prevent clogging or contamination downstream. As you can see on the image, there are a number of tank solutions available to engineers and urban designers, both natural or engineered structures. Some of the engineered tank solutions include cast-in-place, precast concrete tanks, arches, and plastic structures. We'll focus today on just plastic stormwater tanks. These can be easily integrated in a stormwater management plan for the infiltration, retention, or detention of surface water runoff. Detention systems, they're also known as attenuation systems. They're designed to spread the peak flow of a storm event. It does this by holding and releasing stormwater slowly. As I mentioned before, the idea of this is by controlling the runoff to reduce the risk of flooding downstream from a development. A retention system collects and stores water permanently for reuse, for example, to water things like landscape areas. Infiltration systems or soak wells are used a lot in sandy areas to temporarily store water to allow it to naturally seep back into the ground to replenish a dropping water table. To illustrate this, retention and infiltration are two common adaptations of these tanks to make best use of captured stormwater. Retention for irrigation or reuse purposes, infiltration where the soil can naturally free the water from its impurities. In both cases, the water is used at or close to the source of collection without it flying through to any downstream infrastructure or receiving waterway. But if discharging into downstream infrastructure is the objective, then as I explained before, detention gives designers the greatest control over the quantity of water to enter it. In very simple terms, it's an easy calculation. Before I go on, I want to make special mention on two types of hydraulic control structures. The first are stormwater treatment devices. These are located upstream of the tank, with their performance being individually assessed and governed by the EPA and local DA requirements. And depending on project requirements, there are many types, from gross pollutant or silt traps, stormwater filters, or even light oil separators where hydrocarbons exist. The other type of hydraulic structure are flow control devices, which, as the name suggests, control the release of water to prescribed rates downstream of the tank. These are typically installed in chambers with either purpose-designed mechanisms or just a conventional orifice plate. Now, both these hydraulic control structures are not the topic of today's presentation, but I want to mention them as they are essential elements that affect the quality and quantity of water being discharged off the site. I want to go back to this slide to give an overview of the storage options available. From the top, we've got a detention basin. You often see these used in low to medium density areas. They tend to take up space that could otherwise be used for urban or commercial development. Then next are concrete tanks, normally expensive to construct and transport. Next along are the plastic arch systems, which require a decent amount of space. And finally, plastic tanks. And within this large category, there's a huge range of options, with not all being equal. So today, I'm only going to focus on plastic tanks that can be assembled into producing underground cells for stormwater. These can be adapted to a softscape where infiltration can be achieved. Here you can see them assembled, wrapped, and backfilled. They can be installed under slabs in commercial and industrial applications where space is a premium. In fact, geocellular plastic tanks are installed in lots of projects, from car parks, driveways, in landscaped areas to commercial buildings, industrial areas, airports, and even military bases. In a recent installation, here is an example of a tank being used for infiltration at a school in WA. Now, in this case, designers required a high-capacity tank to resolve a drainage problem, specifically to collect the excess surface water in a specific area of the school. The tank was positioned, then wrapped with a purpose-built permeable geotextile. This allowed the water to gradually percolate into the water table as it was being filtered by the geotextile and then the soil. This is an example of a tank being used for both infiltration and detention in Canberra. The purpose of the tank was to manage the runoff from the car park. Two different tank systems were installed adjacent to each other to work in series. One was an infiltration tank and the other a detention tank. In the industry, there's a wide range of options for plastic tanks. The two on the right are typical of plastic crates. The one on the left is typical of a modern geocellular unit. I'll start with some general comments. Unlike concrete tanks, plastic tanks are versatile. They can be cut and joined, and the structure can be readily used for infiltration. Good designs have a high void ratio and can connect to large inlets and outlets that can be easily inspected. Good designs are also load rated and hold their strength over time. But there are plastic tanks that are poorly designed, manufactured, difficult to access, monitor and maintain. And unfortunately, these give all plastic tanks a bad name. And finally, the engineer has a responsibility too. Despite the design or make of a tank, these products always run the risk of being poorly integrated in a stormwater management plan. So when specifying plastic tanks, there's a number of things to consider. Councils, through their development control plan, will enforce compliance to regulation. They will specify the methods an engineer needs to use to ensure the property meets the stormwater management plan. This takes into account the volume of water that the property needs to manage from the landscape, hard stands, and roof areas. Not only does the certifying engineer need to integrate the tanks properly, but as with all key stormwater products, the structures themselves need to meet minimum strength, durability, and quality requirements. In Australia, there are no standards that govern plastic tank systems, and the problem with that is, unfortunately, some manufacturers make claims about strength and design life that just aren't substantiated. However, there is a UK standard called SIRIA, which is specifically written around geocellular tanks. It gives guidance on testing, structural design, construction, and installation. This is the gold standard to benchmark performance, and as such, manufacturers should qualify their product to this standard to ensure that failures don't occur and a design life is maintained. We encourage you to expect compliance to this standard when dealing with a manufacturer. A structural design should consider the load-bearing capacity of the tank. The stronger the tank, the shallower it can be buried, resulting in reduced construction costs. What determines the depth of cover required are things like soil type, tank design capacities, groundwater level, pavement thickness, and design loads. SIRIA identifies these as the main factors overlooked that contribute to failures. And manufacturers must be able to come clean on their strength data, prove it with independent testing. To address this, SIRIA have detailed all the requirements for laboratory strength testing. And when considering loads, both short and long-term loads must be addressed. Dead loads include the mass of soil surrounding the structure, plus the weight of slabs or anything else permanent that a tank will be subjected to. Live loads are temporary loads like vehicles, which also need to be considered. Tanks that have vertically aligned load-bearing pillars offer a fairly decent vertical strength and stability, and manufacturers should be able to provide you with independently tested vertical load results. Lateral loading is as important as vertical loading and takes into account soil mechanics. This is a key driver to how deep a tank can be installed. Be aware that specifically in high water table applications, tanks can be pushed out of the ground. So in these instances, either locate the tank close to the surface to avoid the water table, or locate the tank beneath a heavy pavement to anchor it down. Also, great emphasis should be placed on the jointing methods. Systems that use a combination of cross and brick bonding allow for a more rigid tank construction. Again, manufacturers should provide independently tested and certified lateral load data. This is to justify the installation depths that they recommend for your project. To illustrate to you that plastic tanks in the industry can vary in strength, our office in the US ran some comparative testing. And if you enjoy, like me, seeing structures getting destroyed, you'll like this video. Note some of these products are now sold in Australia.
We've independently tested 7 products to destruction in both vertical and lateral planes on 2 different test rigs due to size constraints. These tests allow us to simulate a static load and a dynamic load. We are testing ACO Stormbricks HD, ACO Stormbricks SD, Graph Eco Block, Brentwood Storm Tank, Oldcastle Kudo, Eco Rain Tank, and ACF R Tank HD. We see the failure mode of the Stormbricks HD system at a maximum load of 86,784 pounds. We see the lateral failure mode of the Stormbricks HD system with a maximum load of 16,424 pounds. We see the failure mode of the Stormbricks SD system with a maximum load of 72,291 pounds. We see the lateral failure mode of the Stormbricks SD system with a maximum load of 28,489 pounds. We see the failure mode of the Graph Eco Block system at a maximum load of 59,728 pounds. We see the lateral failure mode of the Graph Eco Block system with a maximum load of 5,514 pounds. We see the failure mode of the Storm Tank system with a maximum load of 48,503 pounds. We see the lateral failure mode of the Brentwood Storm Tank system at a maximum load of 14,545 pounds. We see the failure mode of the Kudo Cube system with a maximum load of 19,915 pounds. We see the lateral failure mode of the Kudo Cube system with a maximum load of 2,956 pounds. We see the failure mode of the Eco Rain Tank system with a maximum load of 7,469 pounds. We see a lateral failure mode of the Eco Rain system with a maximum load of 5,747 pounds. We see the failure mode of the R-Tank system with a maximum load of 12,750 pounds. We see the lateral failure mode of the R-Tank system with a maximum load of 14,014 pounds. ACO Stormbrick systems outperform all others in both vertical and lateral testing. We hope you keep these results in mind when specifying your next geocellular stormwater storage system. For more information on testing of geocellular systems, contact us at acostormbricks.us.
Okay, apologies for the imperial units, but I just wanted to show you that plastic tanks in the industry can vary in strength significantly. Okay, some manufacturers have a tendency to only disclose the short-term and not the long-term test results of their tanks. Products need to be able to sustainably support loads over the design life of the project. This is crucial for a durable installation. Tank materials are liable to creep, meaning they deform over time, and products must be strong enough to withstand this. The long-term strength test data allows manufacturers to determine the design life of their tanks. Not appreciating long-term strength can have extreme consequences. This is an example of an installation where the tank has failed because of creep. It's really everyone's nightmare and just highlights the importance of long-term strength. For tanks, the hydraulic capacity refers directly to the volume of water that the structure can store, and different tanks in the industry will, of course, offer different capabilities. You can optimize the capacity of the tank by selecting products with high void ratios, which is over 90% for geocellular systems. Having such a high void ratio reduces excavation and obviously the construction costs because of that. Now, arch systems, for a quick comparison with geocellular systems, have a void ratio of around 50%, which essentially means the excavation needs to be almost twice the size. Arches hold water in the open space beneath them, as well as in the voids above them between the stones. This really isn't an efficient way to hold water, not to mention the additional cost of the stone fill. On the screen is an example of two tanks side by side, offering the same storage. And as you can see, the installation volume of the geocellular tank is considerably smaller. As another comparison, let's look at concrete structures. Although concrete tanks provide 100% water storage inside the tank, they do have thick walls, which reduces the void ratio to around 80%. And they're expensive to build and install. In comparison, geocellular tanks are more economical while still providing a high amount of storage. For concrete tanks, they're obviously round, but they need square trenches. Each pipe needs to be have 250 millimeters of sand or stone bedding and around half a meter spacing between each run. All of this increases the excavation required and means more fill, making the installation bigger and more expensive. A good manufacturer should be able to help you optimize the space while helping you meet the storage volume requirements of the project. A tank versatile enough to shape itself around your project will give you more options to meet a site's storage requirements. Modular tanks offer the ability to adapt themselves to an underground space with some level of flexibility. This is particularly useful when avoiding things like existing services, buildings, or footings. Manufacturers should give you tank layouts to help you navigate the physical constraints of your project, as well as clear installation instructions. As I mentioned earlier, tanks can perform any or a combination of these roles, and depending on how a tank is used, it requires a different type of wrapping. In non-sensitive retention or detention applications, geomembranes are used as the bladder for storing water, along with the geotextile on the outside to protect it. Now, as long as minor leakages from the tank can be tolerated, the membrane is normally just taped together. This is used in the vast majority of applications. But for sensitive applications, like a tank positioned close to a building or to simply contain contaminated runoff, we'd recommend using a welded geomembrane installed by an accredited contractor. This ensures water tightness. But as before, the geotextile wrapping on the outside only needs to be taped. The focus in this instance is on the integrity of the membrane. And for infiltration systems, there's no membrane used, just the geotextile, which acts to minimize the sediment buildup within the tank while allowing the water to percolate. Stormwater tanks can be very large, and moving them to site and then into the excavation can be costly. Geocellular plastic tanks are lightweight to transport, and the modules are designed to stack inside one another, which means they take up significantly less space compared with other products. This leads to fewer trucks to site and fewer trips to the excavation. Not only is this more cost effective, but better for the environment. The site itself should be considered when selecting a product. The time it takes to store and assemble these tanks can significantly affect construction costs. Some tanks need storage, and worse still, some tanks simply don't stack. Some plastic crate systems are generally assembled away from the excavation, then lowered into it. There are additional rent and labour costs associated with building and storing the tanks before the installation. Geocellular stackable tanks, however, are really beneficial for sites with restricted space or labour, in that they can be built directly inside the excavation. And this video shows the speed of these tanks compared with a traditional crate system. On the right, Darren is building a geocellular unit using a brick bonding method, and on the left, he's assembling a flat pack crate. You'll see that for the geocell, it has 3 times the volume capacity of a double crate system. So crate systems have substantially less capacity and take more time to assemble. So to get access to a tank, a dedicated entry point for both inspection and cleaning is needed, like the inspection chamber shown on the top right of the slide. For inspection and maintenance, open cellular tanks provide uninterrupted access from one cell to the next. This is in stark contrast to the closed-in structures of traditional crate systems. A tank that can't be maintained actually serves no purpose at all. Cameras and jets must be allowed to pass throughout without restriction. And here is just a short video showing how a camera was used to inspect a geocellular tank under a pedestrian precinct. You can see the camera move through the system easily without being restricted by any physical barriers of the tank. On the bottom left, you'll notice a chainage counter showing the distance travelled by the camera cable from the manhole. And so we've now come to the end of our presentation, but to summarise, these are the key things to consider when specifying tanks. From compliance to legislation, the tank's design and strength, the void ratios, how easy it is to transport and ease of access, inspection and maintenance. So now this ends the formal part of our CPD. A little bit about us. These are our products for external applications. We offer trench drains designed for buildings, urban and civil infrastructure projects. ACO Access is our range of manhole covers, and ACO CableMate is our range of cable pits. Our own geocellular tank is called Stormbricks. We have 2 versions, SD for vehicles up to 9 tonnes and HD up to 30 tonnes. Details of this product range can be found at acostormbricks.com.au. In terms of product support, we can offer you a personalised service to help you optimise your tanks. For your specific projects, this involves us configuring the tank and providing you with a part schedule for that configuration. We can also provide you with structural calculations to help in your design to Syria C680. In fact, we're here to help you across the board with all of our products. askaco.com.au is where you can find all of our free project services. These are designed to complement your own project-specific calculations. Thank you so much for your attention today. I feel privileged to speak to you and share the space with Isan. I'll make sure our post-webinar email to you contains all the links necessary for you to learn more, or simply just reach out to us when you need to. I'll now hand you back to the EA team.
Thank you, John, for your presentation. Our speakers will now come together to take questions. So it's the time of the day where you, our audience, can get involved. And I'm seeing quite a few questions come through already via the chat box. But if you would like to submit a question, please do so via the chat. And if you could just ensure that you provide your name and who the question is for. I would also like to welcome to our Q&A today some additional panelists. We have Darren Chan, who's Brand Manager for Civil Construction Products at Alcohol. And we also have John Condon, who's the Associate Director for Civil at WSP, and they'll be joining us today. So welcome to you all. Now, what I might do is I'll kick off with some questions that we've received on registration. So thank you very much for those people who sent through those questions then. And I might start with yourself, John Sordo. So now this question has come from Michelle in WA, and her question is, what rainfall events are your storage cells suitable for?
Yeah, that's a good question. Thanks for that. I suppose you can't really talk about rainfall intensity without talking about catchment areas. These two things determine the storage requirements of a project. I don't know about other manufacturers, but the largest storm breach tank we ever installed was in Belarus at an industrial park called, I think it was called Great Stone. The size of the tank was about 21,000 cubic meters. So really, there's no reason we can't go even bigger than that. Of course, you'd need lots of access points. But having said all of that, you know, in a lot of instances where the catchment hydraulics and the topography lends itself, you can have more than one tank on site, and generally at opposite ends. But really, there's no upper bound limit in terms of how much rainfall these tanks should be able to take.
Okay, thank you. Kind of off the back of that question, I should ask if anybody wants to add to that answer, please just jump in. But we also had a question which came through on registration, and it was around, is underground stormwater storage more suited to new large-scale land developments such as residential subdivisions? So Isan, I don't know if you wanted to jump in first potentially on that one.
Yep, sure. Just unmuting myself. Yeah, so that pretty much depends on the storage, on the geology actually of the site and the footprint of the building. So landscape areas probably depends on how much landscape you have, the cost, and the environmentally sustainable development that the plan that you have. Large scale subdivisions is very unusual to have an underground tank, but especially yeah, storage for reuse is best done above ground and individually, like rainwater tanks for each house. But yeah, a large scale tank of any type would be under municipal land, such as parks, ovals, or things like that.
So I said something, Darren, I did see a question which did come in on registration. It was asked about, for single dwelling residential projects, can they be used?
Yeah, for single dwelling projects, like all different size applications, you can use these tanks. It can be a small residential lot. It could be an apartment building, a big unit block, commercial area, industrial area, even up to big airport infrastructure where you'll have different size tanks. But yeah, definitely you can use these I suppose systems for because they're made modular. You can make them as small as you want. I suppose the smallest that ACO offers is 1200 millimeters by 600 by 300 deep, and then from those little modules you can build up bigger ones. So it's just like I suppose with the ACO system, Stormbrick system, it's like a Lego system. You can start putting them together like Lego and build up a bigger system. So from your single dwelling, you'll just need a small tank, depending on the size of the, I suppose, the area of the land that you're developing. And then as you go up, you'll get bigger tanks, and with the flexibility of these geocellular tanks, you can make different shapes, different depths, different widths, different lengths, just to fit in the area that you need to, I suppose, hold and store water, and detain water, or reuse the water. So yeah,
Awesome.
they're very flexible, these products, and yeah, can be used for all different sizes, even single dwelling residential projects. But on touching what
Excellent.
Ethan was talking about in regards to, I suppose, the big residential developments, a lot of councils like to see green areas too, and a lot of these, I suppose, you'll see in parklands where they'll have big detention basins. So whenever it rains a lot, these basins will fill up, and then they'll have these grates and control devices that'll let the water out slowly. You wouldn't really build underground storage systems for like residential lots. You'll see a lot of rain gardens, big storage, detention basins like that in those areas. But yeah, for private properties and all that, that's where you'd use these geocellular systems.
Excellent, thank you. We've had a couple of questions come through around climate change or flash flooding. So I'll try to combine the questions that have come through. So the first one, with climate change impacts so prevalent, extreme weather events are becoming more frequent for areas within Australia. So, certain areas which were never flooded are getting flooded. So what design changes are being implemented? And maybe, Isan, I might kick off with yourself, and then we can check in with everyone else.
Okay. Yes. So yeah, that has become into the picture in the recent years. Of course, we have a more intense rainfalls, and as more burst, higher burst. It's what we do actually in design. We will incorporate that factor that for RCP 8.5. I think I usually get it with the worst case scenario. So we'll just increase that intensities by a factor, usually is 20-30%, just to consider that changes that we have in the intensities. So these days, when we are designing, we make sure that have that factor in, so we consider the climate change for the future.
Excellent,
Just to
thank
add
you.
for Isan, just to add to what Isan said, yeah, look, I suppose with climate change on these flash flooding, we're probably stuck with infrastructure that was built a long time ago that didn't have that in consideration. So as all these larger rainfalls, flash flooding occurs, I suppose the old pipe systems that have been in the ground for well over a few decades, it's not able to cope with it. So I suppose it's really down to local government, council areas to build more infrastructure to slow down the peak flows, I suppose, so it doesn't cause the flash flooding that we see today.
Cool. Okay, I've got another question for you, John Sordo. And this question is from Hilton, and it's come through live today. And there are a heap of questions coming through live, by the way, so thank you to our audience. But his question is, John, do you use a design hydrograph to determine storage quantity, outflow, and possible use of water?
Yeah, as a manufacturer, we tend to stick in our lane. What we do get from engineers are things relating to the storage tank specifically. Things like how much volume they need stored, if they have preferred tank dimensions, number of access points, the size of the inlet pipes, size of the outlet pipes. And then we would ask them things like things that are very specific to the application, regarding what type of traffic is anticipated in the short and the long term. and also things like the type of slab, anything that will help us put together a fairly precise recommendation. But we don't get involved with a lot of the planning for that project.
I also have had, there are quite a number of questions coming through around Australian standards. So I'll just kick off maybe with yourself, Darren, which was from Anthony in Victoria, I should say. So thank you, Anthony. Is certification of products to Australian standards mandatory, especially for imported products?
I suppose in the ideal world, we'd like everything to meet a standard, especially Australian standards where we work and live. But in reality, the only really standards that we must comply in most developments is to what the NCC, the National Construction Code, and the BCA, Building Construction Code, and the PCA, all those kind of things are sort of mandatory. In regards to these type of products, I suppose there is no Australian standards, but the Australian standards can be put together, but we would need the help of stakeholders to put a proposal in with standards and for the requirement of this, to how it helps the community, and then it needs to be backed up by other associations. So something like the Stormwater Association or the local government authorities, EPA, Water Services Australia, all these kind of people that have stakeholders in, I suppose, water. If they get together and put in a proposal, I'm sure an Australian standards will be written around. And then, with Australian standards, there is standards around the world that have been written. I suppose it's down to the committee from that Australian standards that's formed that will look at using whichever standard, look at those standards and what is the best standard and write that around for the Australian standard. So it's, I suppose it would be great as a manufacturer. We would love an Australian standards. It'll give us some guidance. We would know what we have to meet, the benchmark that we've got to design our products to, and to what it needs to be tested and qualified against. But without that, as ACO, we're in we're a worldwide company and in a lot of markets. So I suppose, our Stormbrick system have got BBA approval in the UK. It's got MFPA approval in Germany. It meets ASTM standards in the USA. So, if there was an Australian standards that was, we would, in our office here in Sydney, we would definitely put that through the Australian standards and get it third-party certified by any of the certification companies that would do it. So, I suppose, if there was an Australian standards, it'll be great. Then that'll set a benchmark for all products, even Australian manufactured, imported products, to be tested and certified against.
Awesome, thank you. I've got a question which I'm sure that Darren and Isan, you both might want to jump in and answer this one. And the question came from Nigel here in Queensland, so thank you, Nigel. What treatment is required for stormwater prior to storage? So, Darren, did you want to kick off that one?
Yeah, well, I suppose it really depends on the environment where this where it's installed. I suppose if it's a leafy environment or environment that's got a lot of rubbish, then you put in treatment devices like GPTs. If there's going to be a lot of silt runoff, you put in big sediment traps, silt traps. If it's in an industrial area, you'd put in a light oil separator. So there's all different types of treatments, and there's also stormwater filters to do that too. So it really depends on the environment and what you're trying to clean, and you'll probably be guided by the local government authority to what quality they want the effluent or the water to be discharged out. So that would depend on what treatment device you would specify and install in that application.
Excellent.
Yes.
Isan or do you want to jump in?
Yeah. Yeah, I can. So that depends mostly on the storage type, right? So if because most of the pollution is generally treated in 3 months flow. So if, for example, if you have a rainwater tank, you probably want it to have a clean water in it. So we just solely connect the roof drainage to it, not like a car park. And then for the bigger like a stormwater sorry like for a detention, we ideally like to have some kind of treatment at upstream, so just to treat water before we release it.
Thank you. I'll move on to another question. And this one came from Sophie, and she's watching today live. Are there any lessons learnt for the maintenance from the previously installed underground tanks? So I might throw this one to potentially Darren or John Sordo to answer.
Yeah, I can take that one. I suppose with ACO, we weren't the first to be in this space in regards to a geocellular system. There's been many products that have been, I suppose, used for over 20 years now. And I suppose the lessons learnt is that we found that some of the older products that have been in the market for a while, they're sort of like a crate system, a flat pack system where you just build these boxes and then you put these boxes together and then you put them into rows and along the length and the width of for the tank. So as you could appreciate, if there's water going in, the water will go spread out through the cells, but when it comes to maintenance, you can't really get to each cell. So the lessons learned there was that those kind of flat pack systems, you can't really get access to it and maintain, which what happens is gives the design, it shortens the design life of the tank. If it's in a area where it's very silty, a lot of sediment, that could get into the tank, and it could start building up. It could start clogging up your inlets and outlets, and there's no way to get in there to flush it out. What we learned from that was that access and maintenance is a key for these products, and we have developed a pillar system. You would have seen in John's presentation on a video of maintenance where that was going in between the pillars of a Stormbricks tank, and it was fully open. You can see that the camera can go in between the pillars and can go from one end to the other if I suppose your camera can allow that. But what that allows you to do is to inspect the tank to see what's in there. If it's starting to see a bit of silt building up, it's starting to get a bit high, what you'll do is you can put some high pressure hoses in there, and what it does is you'll turn those on and break up the sediment, and that'll make it suspended in the water. And then what you'll get is a vacuum pump truck, a sucker truck, to come in and then just empty the complete tank. So that'll take out all the sediment, and then what you'll do is you'll just fill it up with a bit of water again, see and inspect it, and see if there's any more, and then do the same thing if you need to clean it out a bit more. But with those open pillars, that's our design that allows for complete access and maintenance. If you've got some very special cameras that can go around the pillars that are remote controlled, you can do that, and you can inspect every corner of the tank if you need to. But with the pillars, you can run it down, you can inspect the tank, and with I suppose our system to the Stormbrick system, you could put access points anywhere in the tank. So if you've got a small tank, you may need just a couple at the inlet and outlets. We propose an access unit, so you can get in there, you can inspect the pipes, you can then run some cameras along the tank to check all that. If you've got a really big tank, you can just put the access units at certain intervals, so you can get access in between the inlets and outlets, and then inspect the system to make sure it's all functioning. It's not blocked. It's not filling up with sediment, and have it cleaned when required. So I suppose the lesson learnt from the earlier designs is access and maintenance is very important, I suppose, and that's very important for the asset owner. What they want is a very long-lasting tank. If you're using the old systems, it's really down to what's being collected, and if it's in a dirty environment, then it won't last as long as the design life that was expected.
Great answer. Thanks, Darren. I've got another question, and this one might be for you, John Sordo, and it's from Jeremy watching live today. Hi, Jeremy. Now, his question was, can water be stored within the columns of the storm bricks?
Yeah, that's one of the innovations I suppose we brought into geocellular tanks. The pillars are hollow, and so they offer the additional capacity to store water. And of course, when you take material away, you've got to make sure the whole structure is strong enough, which it is in our case. So the answer to the question is yes.
There was quite a few questions came through. Oh, sorry, go, Darren.
Yeah, just to add to that, I suppose with the pillars, there are weep holes at the top and the bottom of the pillars, so that allows the water to slowly seep in and fill up those pillars too, and to get the void ratio that we say with our storm bricks tanks, you get 97% storm void ratio. So 97% of I suppose the volume of the area that you have for the tank can be collected for water. So those that's things that we've designed in to have that extra capacity.
Peter McGowan asked a question again on the bricks. How are the sides sealed on the bricks? I hope that makes sense.
With the sides, I suppose, well, you can see the open structure. That's the main bodies that you'll see, but we have side panels too. So the side panels just clip onto once you build the main structure, you just put the side panels on. They clip on. Even at the top of the pillars, we've got top covers that cover it. What you want to do is have a nice flat surface when you wrap these geocellular systems up with your geomembrane or geofabrics, depending on what it is. If you're going to use a detention system or geofabrics for an infiltration system, but it gives a nice flat surface to wrap things. And we can also provide pipe connectors through those side panels to connect up with inlets and outlets. So it's very versatile, and it's very easily cut, and you can put your pipes up again. So the side panels just required on the perimeter. You don't need any internal panels. It's all open inside. It's just around the perimeter that you'll have your side panels.
And keeping going with the questions on the storm bricks, is it possible, and this came from Hamed, sent this one through, also, is it possible to detach the elements and reuse the tank for different sites?
Yeah, well, usually if you're using these are pretty permanent. They're going to be, I suppose, installed. You're going to backfill it. It's going to, it's there to do a job for the life of the pavement or the structure that you've built. So, in regards to taking it apart, you wouldn't take it apart. I suppose if the life of the product is finished, the project's finished, you're going to dig it up. The good thing about it's made from polypropylene. You can recycle the material, and it can be repurposed for something else. But in regards to pulling it apart, you wouldn't be doing it to use it for another tank, I suppose.
Thank you. And there was a couple of questions around the recycling, so thank you for picking up those questions as well in that answer. Now, I had a question come through from Amanda, and her question was, how do these tanks go when there is an earthquake?
Well, I suppose it depends.
John Sordo, you take that one.
I was just gonna say it really depends on the size of the earthquake. The units, when they're assembled into a tank, they're not 100% rigid like concrete. So there is some sort of movement tolerance between the interconnecting units. I suppose the key thing is the integrity of the membrane. The membrane can't be ruptured, and there's a little bit of tolerance. I have to be honest, we have never tested it in an earthquake scenario. I dare say if the earthquake is big enough, it'll do a lot of infrastructure damage, tanks included. But, in terms of, movement, subterranean movement, it will move along with the movement. It's not going to rupture as if it was some sort of rigid element that has no tolerance to movement. There's enough of these interconnecting modules. They'll just, they'll move relative to each other, and they'll still stay in position. They'll still stay connected, which is one of the reasons why you can't undo these things, because once they click into position, they're there for good. But they can move around a little bit. The membrane itself, is of a material that allows for that. But, it depends on how big the earthquake is.
Fair enough. I will jump into another question if no one else wanted to answer that one. But this one came through from Carl and Victoria, and it was, please can you address heavy vehicle loading, including forklifts? And that one, Darren, I'm hoping you could jump in and assist with answering that question for me.
Yeah, I suppose when we're talking about, we saw a lot of, in John's presentation, a lot of the testing that was done with different types of products. So that's really direct testing of the product, and that gives a sort of a strength of it. But in reality, these products are installed in the ground with a bit of backfill on top, a cover. And I suppose when you're talking about heavy vehicles and especially forklifts, your slab will be structurally designed to take a load, and that slab will bear a uniformed load onto the storm bricks. So it's not going to be a severe, I suppose, as a compared to a direct load. But also, these have been tested against this Syria C680, which is a UK standard that sets out the testing requirements and structural design. So, in our UK office, they have got the BBA certification for the Stormbricks product, and they've been tested, vertically, laterally, and also had creep tests for long-term loads. But with those heavy loads, if you're going to have a heavy load, you'll have a slab that has been structurally designed to take that load, which would spread that load over a bigger area. Therefore, the actual load at a specific point on the Stormbricks tank is not as large. It's been distributed across a bigger area. So so that, I suppose that's how it how I suppose the forces are passed through from the surface down into the tank.
Okay, cool. Thanks, Darren. I also got a question, and this one might be for Isan or John Condon to jump in with. What are some of the hurdles faced when considering stormwater storage? And they've got in brackets construction and or authority. So, Isan, did you want to, or John, did you want to have answer that question?
Yeah, maybe we leave it to John.
Oh, yeah. That's a nice big open question. Look, I mean, it's like a lot of the guys have said. It's really a response to the design situation that you find yourself in. I think really when you're talking about stormwater storage, you're talking about whether you're storing for reuse or whether you're storing for attenuation. If you're storing for attenuation, then again, you're really responding to the design storms events and the size of the catchments that you're trying to attenuate. So, it's a fairly open question. But in terms of local authorities, really, you're looking for compliance. You're looking for a system that's going to comply with the local authority standards, and you're looking for, in a lot of situations, you're looking for a situation or a design response that's actually going to be something that the local authority might want to take on if it's an adopted asset. So if a local authority is going to take this on, say, as part of the handing over of subdivision assets or parkland, then you really need to design it so that the local authority can take it and maintain it as it'll be their own for the life of the product or the life of the design response. So I think, when we're talking about local authority requirements, it is in terms of the life of the asset. You really do need to think about the local authorities a lot harder than what some people might, simply because it is their asset at the end of the day. So while sometimes the challenges dealing with local authorities can be sort of dismissed, you really are dealing with their assets. So we do need to make the local authority the centre of what we're doing with a large detention basin or detention response.
Thank you. I've got another question, and this one was from Kyle Song, and his question was, how do we prevent the clogging of the detention units made of fine grades? I think I've worded that terribly. My apologies, Kyle. But I suppose it's very much around the cleaning or preventing the clogging of the systems. If John Sordo or Darren Chan wanted to jump in.
Yeah, that's correct. It's really down to the treatment that you provide before it goes into the tank. What you want to put into the tank is as clean as quality water, effluent as you can, and you'll put a treatment device, I suppose, before the tank that'll clean it to the quality that you require, for I suppose the local authorities' requirements. With the storm bricks, we don't have actually cages inside the tank. It's all open. You would have seen in the videos and throughout the pictures in the presentation from John that there is a pillar system. So anything that gets caught will sit on the bottom of the tank, and can be cleaned out with, as I said before, with a sucker truck. I suppose more your question is more with the older style designs where they've got the cages, they've got sort of like a milk crate system where you will get. That's another point of blockage, I suppose, with all those mesh cages that can get blocked up, which can further reduce the life of the product. So for those kind of systems, it's hard to clean because once they get clogged up and you don't have access to it, you can't clean it. So that's going to block up very easily and very quickly.
Yeah, Darren, and we always try and get the water quality items upstream of any detention structures. That way we can make use of the silk capture that you get in those water quality devices to reduce the maintenance in the detention structure.
We did get a question from Shulin in New South Wales that's come through, and maybe a little bit broad, but I'll throw it to the panel. What kinds of technology about stormwater storage are currently being developed here in Australia? Maybe
I think anything that helps the designer meet the requirements of a project, where it be hydraulics or strength, and then the contractor being able to install a tank very quickly, to maintenance, access, the ability to inspect. These were the things that we identified, not only in Australia but worldwide, as being the next frontier when it comes to these tanks. And this has obviously come on the back of a very long history of stormwater tanks, even back as far back as the Romans, as Isan pointed out. But we've incrementally learned along the way, and we've got to the place where we are today, where there are challenges from design right through to maintenance. And so I suppose what you see with our storm bricks is our interpretation of what the problems are and how we fix them.
Excellent. Darren, did you want to add to that answer? Very good answer, John, by the way.
Yeah. I suppose any technologies advanced, I suppose probably in the cleaning part, the treatment part, there is a lot of technologies in that area. A lot of different products that are out in the market now. And, as long as they've been tested and can show what quality the water comes out once it's been collected and cleaned, and then through those, I suppose, test data, there are a lot of software programs now that are used that you can plug in and then use the output for your DA approvals, things like the music from eWater software. If you've got cleaning devices that are SQUIDA from Stormwater Association approved, those things are all can be added, and there are, I suppose, little programs that you can use to plug in the data, test results, and show that this product will provide this kind of effluent at the end, and use it for your applications for DA. So there are technologies out there that are helping improve design, I suppose, too.
I think also for any civil engineer, you really need to work with your urban designers and architects to see what open space you can develop. If you're getting on catchment storage, really working with the flow of the water, I think is as important as anything. Just to try and get a response to the stormwater drainage that can be sustainable, and is something that perhaps reduces the need for infrastructure, full stop, whether it's tanks or pipes, just something that really responds to the natural hydrology and reflects that as much as possible.
Thank you. Isan, did you want to add to the answers at all? I think we are getting very close to wrapping up today's session, but did you want to add anything?
Yes, I just wanted to say yes, John is correct. So we just need to get close to the nature as possible and help that hydrological cycle to do its job in the nature. So any product, anything that help us to get closer or to get to that pre-development condition would help us with the environment and with our design.
Awesome. Look, I think that's all the time that we have for today. So I would invite the audience to join me in once again thanking Isan Bahran, John Sordo, Darren Chan and John Condon for their time and insights shared with today's session. I would also like to thank Engineer Australia's industry partner ACCO for making our webinar possible. And I would really appreciate your feedback on our program today. So if you could please complete the short feedback form, which is linked in the description box below, because that feedback really helps us to improve and to plan future sessions for you, the engineers. So finally, thank you again for joining us today, and we hope to see you at our next webinar.